energies. So calculate the loss of rotational kinetic energy due to the linking of the probe with the satellite. And this is the same thing, right? We've done this with linear momentum, right? When the bullet flying along strikes the block that's sitting still, there's a lot of kinetic energy lost, right? So some kinetic energy is going to be lost here. So concept zero is kinetic energy is 1/2 I omega squared, right? Okay, so the initial kinetic energy is just this probe spinning. They give you the moment of inertia on the previous page is 1.44 times 10 to the 4th kilogram meters squared, right? Okay, and then they give you the angular velocity in part B, right? Isn't it 16 squared, right? So you're 1.44. So put that in there, right? That's this one, right? And then afterwards, right? So that's your initial kinetic energy, right? And then afterwards, you've got the moment of inertia of the satellite plus the moment of inertia of the probe, right? 1/2 that times the final omega squared, and that's what you got here, right? The final angular velocity. Now I'll give you a clue. The initial angular velocity is 16. This angular velocity ends up being an even number, like, oh, I don't know, something like, 10 or 11 or maybe even 12 radians per second, okay? So it comes out beautifully, right? So this is your final. Notice that there's more mass, but there's less velocity, right? But you will end up losing angular kinetic energy, okay? So again, plug in, this is your initial kinetic energy is just this probe spinning. That's the 1.44 times 10 to the 4th kilogram meters squared, right? And then the final one is the probe is still 1.44. This is the moment of inertia of the satellite. So add those two moments of inertia together, 1/2 I omega squared, use that final angular speed, and then subtract. Go this minus this initial, EK initial minus EK final equals lost. Or is it final minus, anyway, yeah, figure it out. All right, good enough.